press the bell icon on the YouTube app and never miss another update.
Hello students, in the previous class we have discussed about Maxwell's equation, importance of Maxwell's equations and history of electromagnetic waves as well as Hertz experiment, right. Henrik Hertz in 1887 produced and detected electromagnetic waves successfully by using an electronic oscillator, right, electric oscillator we can say, right, called spark gap arrangement, right. It acts as a capacitor as well as inductance, right. So here he could generate electromagnetic waves of wavelengths 6 meter, right. Now further Jagadish Chandra Bose produced electromagnetic waves of 5 millimeter to 25 millimeter, right. So Marconi has produced, and most importantly he is the father of wireless communication system. So using the same arrangement with antenna and ground, he could able to transmit electromagnetic waves through several kilometers. Now we will take some important properties of electromagnetic waves. In fact, most of the points we have discussed earlier in previous classes, but we are summing up at one side at one certain points, right. Now we will take properties of electromagnetic waves, right. Now the first property is that electromagnetic waves consist of time varying electric field and magnetic field vectors oscillating or vibrating mutually perpendicular to each other and also perpendicular to the direction of propagation of wave. If we represent electric field, magnetic field and the direction of propagation, right, on Cartesian coordinate system, right, electric field is vibrating along y-axis, magnetic field is vibrating along z-axis, and the wave is propagating, right, along x direction. In vacuum, speed is maximum c, and in any other medium the speed is less than that, depending upon electric and magnetic properties of the medium, right. Just as we have wave equations in case of progressive waves, particularly, right, in the previous year we have discussed, right, waves, mechanical waves, transverse waves, right, longitudinal waves, etc., particularly sound waves, right, where a wave is represented by, right, an equation called wave equation. Wave equation gives the magnitude of displacement of a particle at a distance x from the origin at any instant of time. So this is y of x and t. It is function of both distance and time. In a similar way, right, the electric field, time varying electric field, right, is given by at any instant of time Ey is equal to E naught sin omega t, right, into kx minus omega t, where it is omega t minus kx, Bz, z component, is equal to B naught sin kx minus omega t. This indicates that with time the magnetic field and electric field both are varying. Here E naught is the maximum value of electric field or peak value of electric field, or it is called amplitude of electric field, right. Similarly, B naught is the maximum value of magnetic field and is also called peak value of magnetic field and amplitude of magnetic field. Here omega is equal to angular frequency, that is, we know that omega is equal to, right, 2 pi f, right, or 2 pi by lambda, and k is propagation constant. The second property is that electromagnetic waves are transverse in nature. The waves which vibrate perpendicular to the direction of propagation are called transverse wave. Since electric field and magnetic field vibrate perpendicular to the direction of propagation, electromagnetic wave is a transverse wave. We cannot find no electromagnetic wave having a longitudinal nature. Now, third one, right, we know that the speed of electromagnetic wave as predicted by Hertz using Maxwell's equations, right, Maxwell, right, C is equal to 1 over mu naught epsilon naught, that is equal to 3 into 10 raised to the power of 8 meter per second, where mu naught, right, is absolute, right, permeability of free space, that's value 4 pi into 10 raised to the power of minus 7 Henry per meter. Mu naught absolute permittivity of free space, its value is 8.854 into 10 raised to the power of, right, minus 12, right, farad per meter. So when we substitute the value, we get this 3 into 10 raised to the power of 8 meter per second. And speed of light is different in different medium, just like speed of sound wave is different in different medium. Now, in any other medium, speed of light V is equal to 1 by square root of mu into epsilon, right, where mu is permeability of free space, right. Now, we can write mu is equal to mu naught mu r, and epsilon is equal to epsilon naught into epsilon r. Now, the fourth property, electromagnetic waves do not require material medium. They can propagate through vacuum. Now see here, now sound waves are mechanical longitudinal waves, right, they are elastic waves, they require a material medium for their propagation because their propagation, right, depends upon the elastic property and density of the medium, right. Similarly, right, electromagnetic waves, right, their propagation through a medium depends upon electrical property and magnetic property, right. When sound wave propagates through a medium, particles of the medium vibrate about their mean position, but when electromagnetic waves propagate through space, right, the particles will not vibrate. The vibration is electric field and magnetic field. They can exist in vacuum as well as in right, material medium. Therefore, light does not require, electromagnetic wave does not require a material medium for its propagation, but it can propagate through vacuum. The reason is that the varying electric field and magnetic field can exist even in vacuum. The fifth property, electromagnetic waves undergo reflection and refraction. Right. When electromagnetic waves fall on a surface, right, now they are capable of reflecting out from the surface. That indicates that, that means electromagnetic waves incident on a surface get bounce back, right? That means electromagnetic waves undergo reflection. Now, when electromagnetic wave travels from one medium to another medium, its velocity changes, right? That means it undergoes refraction. The sixth property, electromagnetic waves exhibit interference, diffraction and polarization. The three important properties of a wave are interference, diffraction and polarization. Interference is the modification in the distribution of intensity of wave due to superposition of two or more identical waves traveling through a medium, right? Diffraction is the phenomenon of bending of a wave, right, around the corner of an obstacle or slit and encroaches into the region of geometrical shadow, right? And polarization is the property of electromagnetic wave by the virtue of which, right, they can have the property of one-sided. That means their vibration can be restricted to a single direction or a single plane, right? Now here all the waves, right, electromagnetic waves exhibit interference, diffraction and polarization. Now we know that polarization is exhibited only by electromagnetic waves. Sound waves do not exhibit polarization phenomena. When electromagnetic wave travel from one medium to another medium, its frequency remains same, but wavelength and velocity change. We know that frequency of any wave is the characteristic of the source producing it. When a wave travels from one medium to another medium, generally for all waves, right, there is no change in frequency. But wavelength of a wave depends upon the property of the medium. Wavelength of mechanical wave depends upon elasticity and density, and wavelength of electromagnetic wave depends upon permeability and permittivity of the medium, right? Therefore, when light travels from one medium to another medium, that means electromagnetic wave, frequency remains the same, but wavelength and velocity will change. Eighth property, at any instant of time, both electric field vector and magnetic field vector are always in phase, right? So generally, when we take the mechanical waves where the particles are vibrating right about their mean position, but when we take electromagnetic waves, there are two vibrations, electric field vector and magnetic field vector. Now they always vibrate in phase. They have same magnitude and same direction, right, at any instant of time. That means not the right numerical value, right. They will reach the maximum value and minimum value simultaneously. And phase difference between electric field vibration and magnetic field vibration is 0. Right. Now, at any instant of time, the ratio of electric field to magnetic field of electromagnetic wave is equal to speed of electromagnetic wave. So, in free space, right, C is equal to E by B. E is instantaneous value of electric field, D is instantaneous value of magnetic field, that is equal to E naught by P naught. They are the peak values, right. Again, this is predicted by, right, and we have also discussed this one, right, while discussing about Lorentz force, right, the force on a charged particle, right, moving perpendicular to two mutually perpendicular electric field and magnetic field, right. Now the speed of the charge moving through the region C is equal to E by B, right. Here also the same thing, right, C is equal to E by B. Now the 10th one, the average electric energy density and average magnetic energy density, right, of electromagnetic wave, right, are equal. The energy density of magnetic field is equal to energy density of electric field. That means we have UE is equal to, right, UB, and that means epsilon naught E naught square by 4 is equal to epsilon it is B naught square by 4 mu naught. This relation has been discussed in previous class just before taking Maxwell's equation, that is, I think it is in part 2 we have derived the energy. Now the property number 11, energy carried by electromagnetic wave is equally shared between electric field and magnetic field. That is, energy of electromagnetic wave is equal to energy of electric field plus energy of magnetic field, that means energy density, right, that is equal to 2UE, that is equal to 2UB. So the energy associated with electromagnetic wave is shared equally between electric field and magnetic field. The 12th one, electromagnetic wave possesses both momentum and energy. Right. Now, momentum of electromagnetic wave. Momentum of electromagnetic waves is P is equal to, this is average energy of electromagnetic wave by C, right. So, a wave generally carries both energy and momentum, right. A wave is a method of transportation where we can transfer both momentum and energy from one place to another place without transferring matter. Here also, right, they possess momentum. Momentum is given by P is equal to UA by V. Now, the 13th one, intensity of electromagnetic wave, I is equal to half epsilon naught E square E naught E square E naught square C, right. Here, electromagnetic wave, when it travels through space, it transfers both energy and momentum, right. Now, when it is transferring energy, the intensity of electromagnetic wave at any point is the average energy, right, transmitted per second per unit area at that point, right. Now, the intensity of electromagnetic wave is given by I is equal to half epsilon naught E naught square C, where C is the speed of light in vacuum, right. And 14th one, now intensity of electromagnetic wave due to a point source of power P and at distance R is I is equal to P by 4 pi R square. Now, we have discussed the same, the intensity of progressive wave, the power of the source of a wave, right, etc. They are having light bulbs, right. Light is an electromagnetic wave, right, which is visible to our eye, and whenever we are bringing that bulb, we are having 60 watt, 100 watt, 1000 watt bulb, that is called as the power of electromagnetic waves. But as we move away from the source, the intensity of the wave decreases, and it is given by I is equal to P by 4 pi R square. Now, we can take here, this is the source P with power P, and it is the distance R, and I is the intensity at that point. If the source is a point source, right, then the energy spreads over a sphere, right, and here I is equal to P by 4 pi R square. 4 pi R square is the area of the sphere over which energy is falling at that point. Now, take some note points. Point number 1, right? Electromagnetic wave exerts a pressure, right, or force on the surface on which they fall. The pressure is called radiation pressure, right? So now when electromagnetic waves fall on a surface, they exert a force, because whenever electromagnetic waves carrying momentum falls on a surface, there is part is reflected, part is absorbed, part is transmitted, and there is a change in momentum of the electromagnetic wave. Now the rate of change of momentum of electromagnetic wave when incident on the surface is the force exerted by the electromagnetic wave on the surface. This force exerted by electromagnetic wave on a surface per unit area is called as radiation pressure, right? Now this radiation pressure is capable of producing motion in an object, right? There is a device called Cook's radiometer, right? It consists of 4 plates, right, pivoted at its center, and it is completely blacked, because we know that black is a very good absorber of, right, radiation, right? When radiation incident on that pivoted plates, they began to move. When we stop electromagnetic waves, right, they stop rotating about the axis. So electromagnetic wave exert a pressure on a surface, right, called radiation pressure. Now the second point, radiation pressure is the force exerted, right, the force exerted by electromagnetic wave per unit area of the surface, right? Now that radiation pressure right, is equal to force by area, that is equal to change in momentum per second by area, right, that is equal to change in momentum, right, by time into area. We know that as the mechanical pressure exerted on a surface is equal to the mechanical force per unit area. And of course, according to Newton's second law of motion, force is equal to the time rate of change of momentum. Here, radiation pressure is the force exerted by electromagnetic wave per unit area, right, of the surface. It is given by radiation pressure is equal to force by area. Force is equal to change in momentum per second by area, or this equal to change in momentum divided by time into area. These relations will help you in solving numerical problems. And of course, in competitive examination, there will be no numerical problem in the main part from this electromagnetic waves, right? But there will be numericals in competitive part, right? Now we will take right part 3a. Now for total absorption, right, radiation pressure is given by Pa is equal to I by C. For total reflection, radiation pressure is PR is equal to 2I by C. Now here we are having the radiation pressure when electromagnetic wave is absorbed by a surface and when electromagnetic wave is reflected from a surface. But take the example of a high quality mirror. When light incident on a high quality mirror, most of the light is reflected. When light, electromagnetic wave incident on a perfectly black body, most of the light radiation is absorbed, right? Though see here, the absorption pressure is equal to I by C, where I is right intensity of electromagnetic wave, and of course C is speed of light. That means the reflection pressure is 2 times the absorption pressure, because right the rate of change of momentum gets doubled, right, during reflection. The change in momentum is equal to mv minus of minus mv, that is equal to 2 mv, right. Now, electromagnetic spectrum, right. Now, the electromagnetic waves produced by various sources of electromagnetic wave have, right, a long or a vast range of wavelengths and frequencies. Wavelength starting from 0.001 angstrom unit to several thousand kilometers, right. Nearly the frequency also very high, from 10 power 21, 24 range to 10 power 4, right. Therefore, based on, right, this wavelength range and this or frequency range, electromagnetic waves are classified into, right, several types. Now they are, right, first one we have gamma rays, Number 2, X-rays. Number 3, ultraviolet rays. Number 4, visible rays. Number 5, infrared rays. Number 6, microwaves. And number 7, radio waves. They can be classified into 7 types, from gamma rays to radio waves, based on the wavelength range and frequency range. Right now, coming to this word particularly spectrum, right? We have discussed in geometrical optics, right? Now, when a white light or a composite light consisting of several wavelengths, right, is made to pass through a prism, right, due to refraction at the prism, refractive index of the prism, right. Now the dispersion takes place. The light splits up into constituent colors. Suppose we are having a pure white light, it splits up into 7 colors, Vib, Gay, Or, right. Now this ordered sequence of colors, right, from violet to red with increasing order, or from red to violet with decreasing order of wavelength, is called as spectrum. Generally in optics, so far we have studied, right. So in optics that deals with the study of light, a spectrum is an ordered sequence of wavelength or frequencies obtained, right, when a composite light is passed through, right, a dispersing medium. In a similar way, right, since this electromagnetic waves have a large, a vast wavelength and frequency range, right. Now here an ordered sequence or arrangement of wavelengths, right, and frequencies of electromagnetic waves is called as electromagnetic spectrum, right. Now among them, gamma rays have the lowest wavelength and highest frequency, and with the go on to X-ray UV rays, wavelength increases, frequency decreases. Radio waves have the highest wavelength and the lowest frequencies. Now we will take this wavelength range and frequency range, that I will write it on the board, right, because it is just a numerical term, right. Now we have now the first one is gamma rays. They have wavelength range from 0.001 angstrom minute to 0.1 angstrom minute, and the frequency range 1 into 10 power 21 to 1 into 10 raised to the power of 19 hertz, right. So the lowest frequency is 0.01 angstrom minute and the highest frequency is, right, 10 power 21. Now the second one, right, X-rays, right. Now they have wavelength range 0.1 angstrom unit to 100 angstrom unit, and the frequency range 1 into 10 raised to the power of 19 hertz to 1 into 10 raised to the power of 16 hertz. Now the third one, ultraviolet rays having the wavelength range 100 angstrom unit to 4000 angstrom unit, frequency 1 into 10 raised to the power of 16 to 8 into 10 raised to the power of 14. Now visible rays, they have wavelength range from 4000 angstrom unit to 7500 angstrom unit, and they have the wavelength range 8 into 10 raised to the power of 14 to 4 into 10 raised to the power of 14 hertz. Next comes infrared rays having wavelength range from 7500 angstrom unit to 1000 micron. 1 micron is equal to 10 power minus 6 meter. Now this frequency range 4 into 10 raised to the power of 14 to 3 into 10 raised to the power of 11. Now we have microwaves. They have wavelength range from 1000 micron to 0.1 meter, and the frequency 3 into 10 raised to the power of 11 to 3 into 10 raised to the power of 9 hertz. Now radio waves, they have wavelength range from 0.1 meter to 10 raised to the power of 4 meter, and frequency range 3 into 10 raised to the power of 9 to 3 into 10 raised to the power of 4 hertz, right? Now this is the electromagnetic spectrum. Here we have arranged the electromagnetic waves in this table with the increasing order of wavelength or decreasing order of frequencies. Now you can remember these values, particularly you better to remember wavelength range, right, of electromagnetic waves. It is quite easier compared to frequency. It is 0.001 angstrom unit to 0.1, 0.1 to 100, 100 to 4000, 4000 to 7500, 7500 to angstrom unit to 100,000 micron, 1000 to 0.1 meter. Now we see that units are different here. Earlier we have taken angstrom unit, then we have taken micron, then we have taken meter. Right, this is 0.1 meter to 10 raised to the power of 4 meters. Try to remember the frequency range also, but however it is easier to remember, right, wavelength range, because we often use, right, wavelength of radiation, right, more than frequency, even in optics also, right, optics and physical optics, we are considering wavelength of light more, right, than frequency of light. Now, let us take this electromagnetic spectrum, that is different radiations of electromagnetic waves starting from radio waves to gamma rays, right? Particularly regarding their discovery, sources, how to detect these waves, right? Properties, right? And moreover applications, right? Now, first we will take radio waves. So, number one, right, radio waves are electromagnetic waves of the smallest frequency or longest wavelength, right? So, radio waves are defined as electromagnetic waves of a smallest frequency and the longest wavelength. Number two, radio waves were discovered by Marconi. Marconi discovered radio waves through which he invented radio, right, where we can transmit messages or information. Third one, radio waves are generated by electronic devices called LC oscillators. Right. Now, in order to operate a communication system, particularly wireless communication, we need electromagnetic wave like radio wave, microwave. Particularly radio wave having lowest frequency, right, is produced by, right, a device called electronic device called LC oscillator. That you can see that LC oscillator, right, in AC alternating current circuit, as well as right, when we are discussing right, electronics, right, now it is not there because the transistor is removed, right. Now, LC oscillator, you know that in Hertz experiment, right, we have used this LC oscillator, a system consisting of right, inductance provided by, right, copper wire and capacitance provided by the plates P1 and P2, but here we are using electronic devices. Therefore, earlier, right, in tube electronics we are using right, vacuum tubes, triode valve, right, and they occupy quite a big space. But after the discovery of semiconductor, right, the sizes of the electronic devices, right, got reduced. Later, the smaller form of radio is called as a transistor radio, right. It is called transistor radio because in transistor radio, right, semiconductor transistor are used instead of vacuum tubes. Fourth one, depending upon, right, frequencies, radio waves are classified into LF, MF, HF, VHF and UHF, waves. Nowadays, the use of radio is very small, and of course, there are some usage of FM radio, frequency modulation. Right now, in wireless communication, that is radio communication, we need different frequencies to have different radio stations. Therefore, we need to have a very large range of frequency. Depending upon the frequency range, they are classified into LF. LF means low frequency radio waves. MF, medium frequency radio waves. HF, high frequency radio waves. Now VHF, very high frequency radio waves, and UHF, that is ultra high frequency radio waves. Right. Now, radio waves are used in commercial radios, televisions, right, and short range, right, citizen band, and navigation. Right. Now these radio waves are used in commercial radios. Earlier, before the TVs, we are using radios. Right, they are one of the most important media of communication, and they are used in TVs. But nowadays, we are also using microwaves and short range citizen band. You might have seen, right, in some associations they have the wireless sets, particularly that policemen, right, they don't have wire connection, right, that has a limited area and limited frequencies, and those sets are called, right, short range citizen band, and they are also used for navigation purpose. Now, let's take microwaves. Number one, microwaves were discovered by Hertz. In fact, Heinrich Hertz in 1887 discovered electromagnetic waves, produced electromagnetic waves. In fact, and those radiations comes in the wavelength range of microwaves. Number two, microwaves are short wavelength radio waves. These microwaves are also called short wavelength radio waves because their wavelength is less than radio waves, but they are also used for communication purpose just as radio waves. Therefore, microwaves are also called radio waves of short wavelength. Right. Now the third one, that we know that wavelength range is from 1000 micron to right 0.1 meter. Now fourth one, they are produced and detected by special oscillatory electric circuits. So namely magnetrons, gun diode, etc. Right. Now they can be produced and detected by oscillatory electric circuit. Oscillatory electric circuit means again LC circuits, right? Now there are different devices called magnetrons, right? Gun diode, etc. They act as source as well as detectors. Now the fifth one, right? They are used in radars, radio detection and ranging, the expansion of radar, right? Now long distance communication, right? Microwave ovens, right? Now the microwaves find their major application in radars, right? So radar is radio detection and ranging. That means the position of aircrafts, right, can be located by using microwaves, right, with a system called as radars, right? You might have seen at the airports and different stations we are having radars. Using radars we can exactly locate the position of the aeroplane, that is what exactly the distance of the plane, and using the Doppler effect we can find in which direction it is moving and what is the speed of the aircraft, right? They are also used in long distance communication. For example, we are having mobile phones, right, etc. And they are used in microwave ovens. Now nowadays we can find micro ovens for cooking purposes, right? It is available in hotels, we can see them in some houses, and even in bakeries. When you take some bread, right, or any other snacks, right, immediately, right, they will be heated and given to it. That device is a microwave oven. Now let us stop at this stage. In this class we have discussed right important thing, the properties of electromagnetic waves, energy associated with electromagnetic waves, momentum of electromagnetic waves, intensity of electromagnetic waves, and the important thing is radiation pressure exerted by electromagnetic waves. And also we have electromagnetic spectrum. So far we have taking from gamma rays to right radio waves, and we have so far discussed two types of electromagnetic waves, radio waves and microwaves. In the next class we will take the other radiation, infrared, visible, and X-rays, ultraviolet rays, gamma rays, etc. Okay.